Now we will start with the TV and PV diagram, since they help us in understanding how the properties will change during a phase change process. First, we will start with the TV diagram. And here in the y-axis we have the temperature, and in the x-axis we have the specific volume. As we did before in the heating experiment of water at 1 atmosphere, we have obtained the following curve. So we started with a temperature of 20 degrees, and as heating started, the temperature increased to the saturation temperature at a pressure of 1 atmosphere, which is 100 degrees Celsius. Once we have reached the saturation temperature, phase change process occurred, and now the saturated liquid is converted completely to saturated vapor. Once the phase change process has completed, the temperature will start to rise again, and until we reach the superheated vapor. So this process was held at a pressure of 1 atmosphere. So if we need to repeat the same process but with a higher pressure, let's say we repeated the experiment in the piston cylinder assembly, but now we added weights on the piston until the pressure here, let's say, is 1 megapascal. And if we want to start at the same temperature at 20 degrees and at a higher pressure, the specific volume now will be less. So due to compression, the specific volume will be smaller than the specific volume when the pressure was 1 atmosphere. So as heating start, the path of the curve will be much like the path of the process when the pressure was 1 atmosphere. But there are some differences. First, this difference, the specific volume will start at a smaller values, and the water will start to boil at a much higher temperature than 100 degrees. The saturation temperature at a pressure of 1 megapascal is equal to 179.9 degrees. So the saturation temperature will be much higher. The saturated liquid specific volume is larger than the saturated liquid specific volume when the pressure was 1 atmosphere. So the saturated liquid specific volume has increased, and the line connecting the saturated liquid to the saturated vapor will shrink, will be much shorter. So the specific volume of the saturated vapor at pressure of 1 megapascal will be less than when the pressure was 1 atmosphere. And when the phase change process is completed, the curve will have like similar path to the curve when the pressure was 1 atmosphere. So as the pressure is increased further, so if we increase the pressure much further, and this horizontal line will shrink more, until it becomes a point. So it will shrink, this line will shrink as we increase the pressure until it becomes a point. This point here is called the critical point. So the critical point is defined as a point at which the saturated liquid and saturated vapor states are identical. So at this critical point, like, there is no phase change. So we did not know we did not see the phase change from liquid to vapor. So instantly above this point, the liquid will be converted to vapor. So there is no phase change, and we cannot see a mixture of liquid vapor at this point. So the temperature at this critical point is called the critical temperature. The specific volume at this critical point is called the critical specific volume, and the pressure at this point is called the critical pressure. So for example, for water, the critical pressure is equal to 22.09 megapascal, or 220.9 bar, and that critical temperature is equal to 374.14 degrees Celsius, and the critical volume is equal to 0.00315 meter cube per kilogram. Now, at pressure and temperature higher than the critical pressure, so in this region, it is customary to refer to pure substance in the region where the temperature is higher than the critical temperature to as superheated vapor. So whenever we have, for example, for water, a temperature of 400 degrees Celsius, 500 degrees Celsius, we can always say, if we know that the temperature is higher than the critical temperature, so we are above the critical point, we can say that we have a superheated vapor. So now if we connect all the saturated liquid states by a line here, this line will be called the saturated liquid line. And the region to the left of the saturated liquid line, this region is called the subcooled region. So this region here is called compressed or subcooled or compressed liquid region. So if the state of the water is fixed by two properties, and this state happens to be in this region, we can say that the water is in a subcooled or a compressed liquid state. If the state is on the saturated liquid line, we can say that the water is in saturated liquid, which means that the water is about to vaporize. So in the subcooled or compressed liquid region, the water will be far from vaporization, as we said before. Then if we connect the saturated vapor points by a line, we will obtain the saturated vapor line. So all states that are on this line will be in saturated vapor state. So this is the saturated vapor line, and to the right of this line, so this region is called the superheated region. The two lines, the saturated vapor line and the saturated liquid line, will be connected and will meet at the critical point. This shape, as we can see here, the saturated liquid line with the saturated vapor line, resembles to a dome. So this look like a dome. Inside this dome, this region here below the dome is called the wet region. So this is called the wet region, or so the pure substance in this region will be in a liquid vapor mixture. So this is also called the liquid vapor mixture region. So this is called the liquid vapor region. So the TV diagram is of great interest since it helps us if we know, like, if we can fix the state of a pure substance by knowing two properties, for example T and V, or T and P, or P and V. So any two properties, independent properties, if we can know their values, we can fix the state on the TV diagram, and depending on the location of this state in the TV diagram, we can classify the state as compressed liquid state, saturated liquid state, or a mixture liquid vapor, saturated vapor if it is on this line, or a superheated vapor to the right of the saturated vapor line, or if the T is higher than T critical, we can also say that this is a superheated vapor. So now we will talk about the PV diagram. Now we will start to talk about the PV diagram. The PV diagram. So the shape of the PV diagram is much more like the shape of the TV diagram. However, in the PV diagram, we will obtain lines of constant temperature instead of lines of constant pressure. So as you can see in the TV diagram, the lines here are lines of constant pressure. So they have like an increasing path, okay, or an upward trend. So however, lines of constant temperature in the PV diagram, so if we draw here the PV diagram, and we'll have, this is the dome, and here is the P, and the x-axis we have the specific volume. So we will obtain lines of constant temperature in the PV diagram. So in order to understand how these lines will behave, we will do the following experiment. So we will obtain water in a piston cylinder assembly. However, we will start with a high pressure by having weights above the piston, and here the water is at a pressure of 1 mega and a temperature of 150 degrees Celsius. So under these two conditions, the pressure of 1 mega and a temperature of 150, the water is a compressed liquid. Since the saturation temperature of water at a pressure of 1 mega is 179.9 degrees Celsius. So in order for the water to start phase change at a pressure of 1 mega, it needs to reach a temperature of 179.9 degrees Celsius. Since the temperature here, which is equal to 150, is far from the saturation temperature, and as we said before, so it's not about to vaporize, and in this case, under this condition, we can say that the water is a compressed or subcooled liquid. So if we want to specify the location of this state, it will be in the compressed liquid region. So this is at the start at a pressure of 1 megapascal. Okay, now we will start decreasing the pressure. So we will remove the weights one by one. So we will remove the weights while holding the temperature constant. If you want to hold the temperature constant, we need to allow the water to exchange heat with the surrounding. If we don't allow the water to exchange heat with the surrounding and we decrease the pressure, the volume will increase, the specific volume will increase, and the temperature will decrease. So we need to add heat in order to conserve a constant temperature process. So because what we're trying to do is we're trying to sketch the constant temperature line. So the T equal 150. So as we decrease the pressure, the specific volume will slightly increase. So during this process, we have a slight increase in specific volume as we decrease the pressure. So when the water reaches this intersect with the saturated liquid line, it will be in its saturated liquid state. So here the water will be in saturated liquid state. So if we want to know the pressure at which the water will be in its saturated liquid state, we need to look for the saturation pressure at a temperature of 150. So in order for the water to start boiling or phase change, the pressure should be equal to the P saturation at 150 degrees Celsius. So the saturation pressure at 150 degrees Celsius is equal to 0.4762 megapascal. So reaching this pressure, the temperature here will be now the saturation temperature at this pressure. So the pressure of 0.4762 megapascal, which is happen to be the saturation pressure at this temperature, and we will now start having phase change. So during the phase change process, we will supply heat, but we will not remove any weight. So during this process, the phase change process, or phase change process, so no weights removal. Why we won't remove any weight? Because simply if we remove weights, the pressure, which happen to be the saturation pressure at this temperature, will decrease. This will make the saturation temperature also decrease, because the two are dependent on each other. So the saturation temperature is function of the saturation pressure is function of the saturation temperature. So if we remove weights during the phase change, the saturation pressure will decrease and the saturation temperature will also decrease. So we will not obtain this horizontal change, phase change line. Okay. And when the water is now completely vapor, so and intersect with the saturated vapor line, it will be in a saturated vapor state. So now if we continue after the phase change process has completed, we can now go back to removing weight and decreasing the pressure. So removing weight and decreasing the pressure, the specific volume will now increase. So the specific volume now will increase in much higher fashion, because in the superheated region, the specific volume is more sensible in change, is more sensible in change when the pressure decreases. So when the pressure decreases, we will have a much more higher specific volume increase than when it was a compressed liquid. So this is the superheated region. Okay. So during this process, this line have a constant temperature always. The water is the water temperature is held constant during all this process and is equal to 150 degrees Celsius. If we repeat the experiment for several temperatures, we will obtain the same trend, downward curve. So this is another T, also a higher T, here T2, higher than 150, and also same trend. This is T3 lower than 150 degrees Celsius. So this is the PV diagram. In the PV diagram we draw lines of constant temperature and they have a downward trend, but in the TV diagram we draw lines of constant pressure and they have an upward trend. So the regions concerned subcooled compressed liquid, saturated liquid, inside the dome mixture liquid vapor, to the right of the vapor dome superheated region, on the saturated vapor curve, the red one, and above the critical point we have the superheated region, is all common with the PV diagram. So here we also have the same regions.